just really nice introduction. Thank you. So I think it's Friday. It's a little bit hard for me, and I think one thing is already have intense work for 4 days, and almost I think you want to see it was a graduate of this course, but I want to see as some introduction. I think a lot of this topic already covered, and other is instructor already is give you a lot of things. So if you say it's too boring, it's just stop me. But one thing I find is interesting is the Bayesian network. There's really like a buzzword, and a lot of things is confusing. Some people talk about Bayesian network, but actually they're talking completely different things. So I think maybe it's a little bit worth to just go to its some fundamentals, see what exactly Bayesian network means. And I'm not going to the detail of some mathematics, because a lot of different branch is very active. One thing it can be talk for days. So I'm just probably going to cover it's a practical things if you want to use, and how to use it, and if you want to see other people's work, you want to see what does that mean when they talk about. So I've just quick over something. It's generally what's a Bayesian network, then how people using Bayesian network, and there's a few example. It's a special part of a Bayesian network, just very, very small branch. And generally it's a training network. If you know the structure, then it's relatively easy. And I think a lot of biology is a focus how to construct a network. But it's a biological network, and mathematics, well, this one computation form is quite different, because there are a lot of things special for the biology. And then I will talk how to leverage some of this thing. It's a network, but it can still capture some special. That's really a dynamic things of biology. So exactly what is the Bayesian network? And in general form is just we'll call it's expert system. It's try to capture everything you know and put in the graphic form. So it's confusing, because from beginning it's confused. There are a lot of things. It's called a Bayesian network. They can call it's a lot of different things. People call it a belief network, Bayesian belief network, or more it's a general. It's called a causal probability network. But actually, this causal probability network is not exactly a Bayesian network. There could be a lot of other stuff. But Bayesian network is a special part of this causal probability network, because it's one part of this graph is called a direct acyclic graph. Generally, what that means is that you have a set of nodes, and there's an edge connect from node to node, but there's a node loop. So a cyclic means from one node, you can never follow the edge, go back to itself. So I talk later, see why this is special required. And then, so there's a graph part, and there's the probability part. So not only have a graph, but it have a set of probability to describe each node, and then this probability table mainly is to describe the relationship from the edge linked to one node. So here is one example of this Bayesian network. The first part is this graph part, and you can see there's the edge only from if you look at the graph, you always can layout from its top down, and the edge always from its top to bottom. There's no edge going back. So that's one is general is a theoretic graph. Or in the matrix form, then generally what means you can put all the node in a triangle form that either is lower triangle or upper triangle. So that means that the edge relationship always go one direction, then from its top down. Then you have this probability table. That means it's everything this node regulated by 2. Then you have the conditional probability table of C condition on its parents. Then for each one, you have its probability table like that. Then this one is confusing. So there's a lot of different form of this Bayesian network. So this one is a tree form. So it's a tree is part of a Bayesian network. So people actually in the literature, people here is a Bayesian network. Then really say I construct Bayesian network like special is a Go annotation. Is people talk about I construct Bayesian network, but actually go deep. Actually, it's just only a tree. So yes, it is a Bayesian network, but the Bayesian network is not a tree. So like this form, you can go from here to here. It's not exactly a tree. So Bayesian network actually capture a lot more than just the standard is tree, what people using decision tree. So I just some is little is the convention how the people it's right about Bayesian network. Generally, there's we already see the graph part. Now is there's the probability. Generally, what that means, you have a node. It's the start that everybody started with the same. You have it's joint probability. So this A is a union of all nodes. But Bayesian network that can rather than it's a direct estimate this joint probability, then you have probably tons of parameters to estimate. Then this one is decompose these things into is a parent-children relationship. So after this decomposition, then number of parameters you need to estimate is dramatically lower. Especially their core is special its property is the Markov blanket, then really it's isolate everything from the other node. That means people always have this problem, say, or only have a 200 sample, but you have 1,000 nodes. How you can estimate that? But Bayesian network, the good thing is that it's a decompose, so everything is a local dependent. When you estimate this one, it's don't dependent all the other nodes, or it's at least one in the Markov blanket, so it's isolate everything else. So in that sense, you still have enough sample to estimate all these parameters. It's not simultaneous estimate 1,000 parameters. So that's why I think this special form is needed for the Bayesian network. And the general is annotation is just you have a node and we have this parent. And some of the structure people talk about is structure is they have a degree. Then generally what talk about is whenever you talk about is all degree, that means you talk about is diverging structure. That means it's one parent. It's simultaneous regulate multiple multiple children. So depend how many children you have, then it's all degree with that. So that is something people call it's a happiness. It's probably essentially the same. When you have it's more downstream children, it's more likely this node likely to be is a key regulator in the biology. So mainly it's called its all degree is high. And reverse that's what it's a converging structure. That means it's have one node. Yeah. One node, you have it's a multiple, it's a parent simultaneous regulate. Then depend how these parent related, then there could be how lot of yeah.
And does this model allow for like a correlation between A and B? Direct correlation?
Actually, no. So that means is you don't need them to be correlated. That one is there's some. That one is what's the relationship between here? If these two are interact, that they don't need to be correlated at all.
But in reality, A and B could be correlated, right?
Actually, a lot of time is that they don't correlate at all. So there's it's later that really is when we call this one A and B, whether it's what form you want to use. If this is a continuous function, if this continuous data, then you can say that's a correlation. But that's continuous data, really they have a lot of different form. Most of the people call a linear Gaussian form. Then everything, if you capture this network using continuous data, underlying model is the linear Gaussian form. Yeah, that's correlated. But there's also a nonlinear function. They're not necessarily to be correlated. So this one we call is the integrity. That mainly is capture how many its parent it has. And we go back. So this one is a Bayesian network. It had to be it's a direct acyclic graph. Then people always ask, why you enforce that? Can you have just other network? It's still called a Bayesian network. So it's fundamental is when we have this joint probability, we have decomposed this its parent-children form. So if you want to remain this is a parent-children form, you have required this is direct acyclic graph. But there's a lot of other research to see whether can you still approximate using this decomposition, but still maintain some of the undirected graph, or it may be a loop. But that's a special research part. But generally, if you want to decompose this one, you have to require this one. So generally here is this very, very simple proof. And as long as you have called induction, then you see as a one node, definitely you can decompose into this form. So a single node, then you can prove that for whenever they have a direct acyclic graph with n node, then direct acyclic graph will guarantee they have a node. There's no children, right? So they have a goal. Don't need to go anywhere. There has to be no children. Otherwise, you always have children, then it can always loop back itself. So as long as there's a graph, guarantee it's no children, then we can separate this one. So either it's a joint probability, then we can just decompose of this AJ, depend on everything A equal AJ, then there's a joint probability of this is A equal AJ. So this one already know that from this one is the net worth n minus 1. So we can know already can decompose this one as this the parent children form. And then the only thing is when you add AJ, you can add, still can decompose this one A and parents, because the only add A is only need to add, only estimate condition probability of this one. So then you can put them together, just like everything include the AJ, but then to a special form, then everything go back. So as long as you have the direct acyclic graph, then it's a guarantee you can decompose this one.
June,
Yeah.
can you back up to the cartoon and point to what is a child and what is a parent here?
So this one is A, this have link, A link to B, D. Then A is the parent, D is the children. But then, yeah, it's very simple. Then it's a condition that, say, in this form, we're talking about this regulation, right? This link, then A is the parent, C is the child. But you're talking about this direction, then yeah, C is the parent, F is a child. So where it's when we talk about children and parent, we really talk about specific. It's a link, yeah, regulation. Yeah. So now there's we can get this one, why we need this direct acyclic graph here. And then we'll see there's the general what Bayesian network can be used. Most of what we call it is expert system. Generally what means is when you have this model, it's a graph plus the probability is table, then if you're given something, you can predict what's the outcome, or it's that means it's information from it's a top down if you see that it's layout of network, or it's a reverse. Most of you see it's something is happened, then you go back, see information, or could be it's a state in their parent. So that means it's a diagnosis, what's the cause of this change. But in the biology, that most of these things, the structure don't know. We'll see what could be its potential, it's a causal relationship, more like it's going here. So we can give it, this one is a, it's a classic, it's a Bayesian network, it's a very simple form. There's a lot of people using this one is for introduction. This one is, I think, very good, simple enough. So it's a burglar system. So you have an alarm set up at home, and whenever they have a burglar coming, the motion sensor detect and trigger alarm. Or you have earthquake, also shake, then it's motion sensor change, also trigger alarm. Then it's earthquake. Now they report everything. You have a major earthquake. You have radio, and there's also internet. Our Caltech capture everything. It's from it's a large tremor to wherever it's a small tremor. But whenever it's an alarm, it's a trigger and give you a phone call. So now it's for you. When you get a phone call, what you want to do? So is go back home, call police, or is it just ignore? So then really it's now the system will tell you what's thing. So first, you have to probably check it's a radio. Check the radio, turn on radio to hear anything about earthquake, or maybe if you have internet, you can check whether internet have report earthquake in the region where you stayed. Then you can infer whether there's an earthquake. If there is an earthquake, then probably you say that's more likely is the alarm is triggered by earthquake. You probably just ignore. Or if there's no earthquake, then it's more likely to be it's a burglar. Then it's better hurry home and at the same time probably call police. So this one is general. It's a expert system. So you already know what's the causal relationship, and then you can also, there's the train, it's a chance of this earthquake. If you have an earthquake zone, there's high chance, and there also is if it's unlikely of earthquake, then the probability of this table relationship maybe get stronger. So that really is a capture not only is a causal relationship, but also there's some is a probability. Then you can adjust train as a different region. So that we'll talk about here. That's a similar that we call is the you have it's earthquake. What that from based on here is the alarm, a radio, internet. Can you is infer what's the state of earthquake? In general, this one is one special form of Bayesian network. Then people is also using is the kind of a buzzword is they train a Bayesian network to do is the classification, but actually this one is not really is a general Bayesian network. Mainly this one we call is the naive Bayesian network. In general, it's just a very, very simple form. One layer of network. You have a parent, you have several of children, and if there's several children, these are independent condition of this parent, then you can just decompose, similar as I've done before, decompose this joint probability into this is a child. It's a parent relationship. Then what the classification or prediction is, when you have knows the children, the result of these children, what is called is observable, then if you want to infer what's the state of this A, in general, that one is just, you calculate is posterior probability of this one is A condition on all these children, so this should have E. Depend on what some is form you can get, you can have its noise all or some other is form, then you can just generate this train. So this one is a Bayesian naive Bayesian net is just one special form of the Bayesian network, similar like a tree form. So yes, it's a Bayesian network, but in general, it's not really, it's a general Bayesian network. So how to train a Bayesian network is generally, first, this part we'll call train is that you already have the structure. Then what you want to train is the probability table. One you have is observation. In general, you have filling the condition probability table. This one we assume that we're in the discrete form, and all this one is node have maybe a 3 state. Then if you have multiple state, then you can consider just to see how many is a cell you need to fill in for this table. So for each observation, you have A to B relationship. Then you can see just one A equal to A1. How many is observation is falling into B1? It's the B2. Then just filling this table. If you have is 2 by 2 state, this one 3 state, then you only have a 2 by 3 table. This one is general 3 by 3. Yeah, so this one you can extend. You have a 5 state, then it's 3 by 5. So this one condition 2 are independent. So you have observation from A to B. Then you have also form is A to C. Then depend on what you want to use. If you just say it's using prediction, it's forward prediction, then you see when your A is in special form is A1, then you calculate the chance. What's one is A1, then you're falling into B equal to B1. So that one is just a reverse, you calculate the probability. Then there's a lot of research on how to fill out this form, whether you have a Bayesian form, whether you have a pseudocount, then there's the ton of research how to do that, or in each specific is a research area, then you have the special form. But in the biology, a lot of this structure we do know, or some maybe is a partial know, and we're interested not is to train the probability table with the known structure, but we reverse the first can you is construct a network to capture the relationship of this node. Some of these nodes can represent what you want to represent. It can be it's a genetics, or it's a gene expression, or it's a protein abundance, or anything. We also have represent the using node represent metabolite abundance. So generally, when you have let's say 3 nodes, then it's you can enumerate all these possible relationship as C, A regulate B, but C really is independent from all these others, or you can have this one that A regulates C, or there are a lot of ways you can think about is whatever drawing, as long as they end up is a direct acyclic graph. As long as you can see from here, there's a node loop, then it's fine. Then this one is a possible. It's a Bayesian network structure. So you can just for 3, probably you can enumerate all these possible things. Depend whether you count at conditional. Whether you can the equivalent structure or not. There will be about. It's some 80 structure, or probably you count it's the equivalent structure to about 20. It's a unique structure. So then if you can enumerate all this structure, then relatively easy. Then whatever the function you know, then it's really end up is a model selection. So you have the data, then you see which is the model fit the data best. Then you can select the model. But in reality, when you have the number of nodes is high, then you can consider all this possible structure, if I enumerate, will be as super exponential. So if there's it go to 6 power of 6, then probably you already have a lose track. All this enumeration. Probably you can draw in the several page, but beyond probably 5 or 6, it's impossible. So in general, this one construct a Bayesian network is generally is NP hard problem. In general, there's a solution you can. Go through all this structure in the polynomial time. So we always have to do some heuristic. So generally, what's the heuristic approach is rather than we go through all these possible structure, we just focus on local structure. So at one time we go through the structure, you select one node that we see whether that's a local structure we can change and make the structure fit the data better. So this one just goes through a loop. The first one is random select a node X, then you already have a parent. Then you can see whether I can perturb this local structure a little bit, see you have a parent. If I remove this parent, do you get a better fit? Or add one parent, does it get better fit? Or I can reverse of this relationship as long as this one still is Bayesian, it's direct acyclic graph. You can estimate the likelihood or see that whether it's fit data. So then we can see all these whether this structure fit the data is better than the original structure or not. Then there's rather than using this deterministic, there are always a heuristic. So whether it's even though you have a little bit worse, you still want to go that is so you don't necessarily to is a trap into is a local minimum. So that one is really then is go to is a little bit complete is branch of is a searching strategy you can using is annealing. So at the beginning as temperature is high, then you can really like it's a random from one is a configuration jump to the other, but at the end then it's probability lower, then really is go to it's more is a greedy search. So there's a lot of things, but in general is as long as you can study is focus one, then this problem is trackable. Yeah, Eric.
So in practice, how many nodes do you start with for that local optimization?
Local is always the step one. If random select this one, then you see whether reject this local change or not. Or if you reject it, keep this form. If accept this form, then you update structure. Then you go back to the structure. Then you random select another node X. It's optimized its local structure. So just go through this loop.
And how many? So you randomly select one node.
Right.
And then how many edges do you allow when you're optimizing the fit to the data?
Each time it's only perturb one, so each time only is perturb one. So either you delete or add.
Oh, just one edge
Yeah, one edge at a time
in the whole network.
in the whole network. Correct. Yeah.
Is there order in which you would do it, or would that matter?
Generally, it's the random. So this one is a heuristic. So the problem is it's a local minimum. So it's better is to go to it's a random.
Do you have a maximum number of nodes or variables you can handle? Do you have upper limit? I mean,
For
can you handle like 10,000 variables in this network?
yes, there's generally we is to construct a network is about is 8,000 to 10,000. Then it really is depend on what infrastructure do you have. So if you want to have just a PC you run, then probably you can handle 100 nodes. If you have a cluster is run for you, then probably it's 1,000. But if you really have it's a supercomputer, then probably you can run through it's 8,000 or 10,000 or maybe more.
But you still have to construct the directed acyclic graph for the whole network if you're just going to randomly select one node, right?
Yeah, so each one, if you consider that have no parent here, then generally all these nodes could be a potential parent. Add node, then you have one parent. Then iteratively, then you're going to accumulate a lot of parents. So like this one is initially you have this only have two parents, and then you say you propose a change at a parent. Then you can see, suppose this one, we just assume everything have 3 states. Then essentially it's estimate the condition probability table of D condition A and B. So the number of parameters you need to estimate is just 3 by 3 by 3. But then it's add one parent, then it's just times 3. So this one is now you can see its number of parameters already changed. So the searching space dimension already changed. So in the statistical form that this one is a jumping. So that's from one dimension form and to another dimension. And if you reverse, then it's a jump back. So there's how to capture this it's a probability. It's a complete branch called it's a reversible jumping, and statistics people already study a lot of this one. But in general form, you can get this model is have a complete different complexity. When you estimate how they fit, it's a data then definitely you have more parameter you can fit data better. Then how to deal with that problem. Either you have go to one branch is the study is reverse jumping, then what introduction is what transition probability, then you can see how likely from is simple form to more complex form, what the other way captured. Then that transition table really is penalize the complexity. But or there's another form, then you can estimate. So this one general is posterior probability of this model you want to estimate how it fit the data. Generally, that relate to is the probability of this model of fit the data. And there's an approximation. It's called a BIC. It's a Bayesian information criteria. You can estimate rather than consider all these model probability that capture the complexity information. You can feed that its maximum likelihood just to see what's the best model given that complexity. What's the best model? Also the parameters fit this data, and then you see how many is parameters you need to estimate that model, and also that relate to number of sample. So there's the base information. Essentially, you can just estimate each one. You have a different model. You calculate the Bayesian information criteria score, the BIC score. Then essentially just minimize the BIC score. That will lead to in some sense, greedy is the best model, but simultaneously is penalize the complexity. So we're talking about the heuristic, and you already asked whether is the order of this one is search make difference or not. Actually, definitely it's make difference. And so heuristic, generally what we do with using is 1,000 different chain. Definitely with heuristic we end up 1,000 different structure. Rather than take them one by one, we average them, see which structure is common among these 1,000 structure. Then we can see what one is more likely to be robust information rather than sporadic or more likely to be a trap in the local minimum. So if you compare this edge and count with the count there is a frequency in the 1,000 structure, then we can get this one histogram. Generally, this one sum of link is very robust. Almost every structure capture that, and some of the is higher. And maybe you have noticed this one generally has 50%. We'll get is a peak. We can talk about later why that actually that's related to some of the information order that order information cannot determine by itself. So by chance, one or the other flip, that's always likely. But actually, you can see most of the time there are some local minimum here. Then everything above this one, we say that's a robust structure information we capture, and all this one is more likely to be noise. We remove that. So after one you get this average structure, they may not end up as, even though we start with it's a direct acyclic graph, but the end result may not end as a direct acyclic graph. So after it's averaging, if you still want to enforce them to be a Bayesian network, you need to enforce them to be a direct acyclic graph. So what we do here is then, given all this node, we can calculate shortest distance. So there's multiple way you can do that. In general, saying calculate distance is just a repeat, it's a metric multiplication. So given all this node, you can multiple different time, then then you can capture all these shortest distance from A to B. So when you have distance matrix, then you can just see is there identify all the possible, see whether from A, is there any path from A back to A, see whether it's A to B, have a step on 2 and B to A get a step into 4, then that means there's a loop from A to B, then back to A. Then if you can identify loop, then you can just trace the what potential is the weakest link, whatever weakest, let's go back to this one is how frequently, how likely it occur in the multiple network. So if this one, the frequency is the lowest, we call this one is the weakest link. Then we remove that link, then go back to step 1, recalculate shortest distance, then see are there still is a possible loop among this node. If there are no, then it end up is a guarantee is the direct acyclic graph. Yeah.
What happens if we don't do this kind of enforcement of PH? Those networks only not mathematically sound, but maybe biologically meaningful?
Yeah, that's a possible. That biological is meaningful because there are a lot of things we'll go later to about the feedback, but generally that will be another is a branch to capture that relationship. But if you start it's a Bayesian network, you want to call it a Bayesian network, it's a better you end up really it's a Bayesian network. Another is a question people constantly ask. So you construct the Bayesian network, we can see there's the parent and there's the complexity. Then people say, can you use it's a 3 parent, can you construct it with a 4 parent? Is your program limit number of this integrate? Actually, yes or no. So you can consider, given this n parent number of parameter, you need to estimate is 3, depend on, we generally assume this one is 3 state. So if you have 2 state, then it's the 2 power n plus 1 is 3 state. We have 4 state, or you can see this parent is a child. They have a different number of state. But in general, you can estimate how many parameters you need to estimate. Then for each cell, how many parameters you get is a robust estimate. So we general rule of thumb is 5 or 10. So if they have a 3 parent, this one regularly simultaneous, regularly 1 child, and in simplest form, this one you have 81. It's a parameter estimate. Then how many is sample you need? Probably about 300 or 400. If less than that, or if it's just only a 300 or 400, it's hard to go to its even higher order. That's a 4 parent. That the data is not going to support any of that structure. So you can limit that itself, or actually mainly is this is data driven. If your data support, you have add more parent, let's go ahead. If no, that only have a couple hundred, you should never go. It's a more complex structure because the number of parameters is not going to have enough sample to estimate this local structure. So you asked about is continuous or is discrete. So there are different underlying. Some is a model a little bit different. So yeah, continuous data, very simple form. People using is a linear Gaussian, and generally what it can capture is only a linear relationship. But also you can using is exponential form that actually can capture its interaction. So yeah, the continuous form definitely can capture its interaction, but consider is compare with discrete form, just using discrete form is generally it's much faster, especially you have a large number of sample, because discrete you have the model complexity don't depend on the model, depend number of sample, but all these continuous data, when your sample get larger and actually calculate estimate the probability that time getting larger, so it's really is proportional to number of sample. And depend on the what model, but discrete, it's very, very easy to capture higher order, so interaction. So even though you don't have a direct marginal effect, you can still capture that relationship. That's more, it's an interaction term. So it's just generally easier, but it's still possible to do. So you really have to get some trade-off. Whenever you have discretization, you lose information. So you lose information, but you get it's easier form, or more is get faster. Or you can go to it's continuous and take a little bit longer. So this one is really is I think it's a personal judgment, or also depend on data, or depend on specific its application. So you can consider what form you want to use. How many time do I have? Okay. So one we call it's a construct structure, especially biology, they always have a missing information. We're not talking about is missing data like a microarray. You have a probe, some gene in some chip. They're always not good estimates, so that's a null value or missing value. When we now talk about it's the missing data in it's a metric form, but really it's the sum of things we cannot observe. For example, this one we have estimate all this gene expression, but actually in the middle, this one is a small, multiplied regularly all this form, but gene expression you cannot observe this one. So if this is a true relationship, but you didn't observe this one, you collapse this to this structure. So now you can see that this structure is not equivalent to this structure anymore, because what from here equal is A conditional on A, B, and C. They're independent. Don't look at this edge. So this structure, what capture relationship is A and B independent conditional on A. So here is A and B conditional on A. They're not independent.
B and C.
Sorry. Sorry, yeah. Yes. So it's B and C, they're not independent conditional on A. So there have be something that really linked if you this truly have the middle. Or something like this one is a alternative form. This one is is a genetic regulate the B and C, but simultaneously there's an environment factor regulate as B and C. So this form, if you only capture A and B, there's a conditional independent, but in reality, in the original true form, they're not. It's independent. So there have to be some link, then really have whether it's a C to really capture all this one, then have to something link here. Either it's maybe it's a C regulate B, or B regulate C, or maybe there's a jump another form as that D regulate B and similarly regulate C. So as long as you have missing information, there's always tricky to estimate what special form. But in some time, if you know that this one is an environment factor, then probably you can propose it's special node that is represent is unobserved. So it's introduce a latent variable to capture all this unknown information. Then it's a construct the structure. Yeah.
So are you saying that you would introduce the latent variable after your heuristic is finished based on expert knowledge, or is the heuristic
So at the beginning, because you have to, if you know that there's some is environment factor, then probably you can give some information. So this one is whenever introduce it's a latent variable, then it's more subjective. Then you have include some prior. That one, there will be it's a lot of way, and I think that will go to very, very tricky part. Yeah. Eric.
Do you enforce a goodness of fit threshold when you're constructing the local structure?
No.
Variance explained or?
Generally, no. And so in the simple, so there's one chain, what we call it's Markov chains. So essentially, all these local structures, then eventually you have a BSC score, just it's using model selection. So as long as it's passed, it's playing better than the alternative form, then you can select. So there's no hard cutoff for the variance plan, just the BSC score.
Of the entire network?
Yeah. So we're talking about the Bayesian network structure is the direct acyclic graph, but in biology, there is not direct acyclic graph. So this one is very, very simple example. You have it's a G regulates C, so they activate it, and then it's a C, it's feedback control. Then both G and C, they have it's a degradation. Then depend on you have a perturbation on G or perturbation on C, then you have complete different correlation structure. So as long as you have this feedback control, then you can make this system stable. So generally we have its activation, then you can have its line represent its regulation, its activation. Then for the feedback control, you can have it's a Hill function represent that, and the degradation form. Then really it's this curve. Then generally it's what you get the static state is this curve is intersect. This represent really is a stable state. So we have feedback. So biology, if you want to get a stable state, you have to get the feedback control. But then interesting is now you can see mainly is you have a perturb either on G or C. Then you have maybe have a different form. So if it's changing parameters on the activation, so this line is you can see it's churn. So it's then you have a different stable state along this feedback control. Then actually it end up is a negative correlation between these two parameters. So interesting, you get activation, but I get negative control. Negative correlation. On the other hand, if you have this one is negative, changing the parameter in its feedback control, then you can see you can shift this curve. Then really it's a stable state. It's along this straight line. Then eventually you get a positive correlation. So in general sense, is all this biological network is context specific. Really depend where is you have a perturbation, whether that perturbation can generate a positive correlation, negative correlation. But for back here, if you say simultaneous changing this one, then you maybe have it's a circular is the simultaneous change this form. Then you have a dot is mainly it's spread around in the circle. Then you end up no correlation at all. So anything that we call is a biological system is context specific. If you have a Bayesian network, it's just it's a snapshot of a specific condition. There's it's a general form. It's with the master is the network and represent everything. So you should always consider what's the context You generate data, and then this data network can represent that data. So do you want to take a break, or you can just finish this part? Or you can come back, finish this part? Would prefer?
Steve's not here, we don't know what to do.
Democratic, you vote. You want to cover break? Finish, okay. So we know that biology is essentially cannot represent by the Bayesian network, and it's only have very, very specific contact to represent. How you can represent this is a feedback loop that truly is biology, and is in some part it captures this feedback loop. You need to go to the dynamic Bayesian network. So there's a lot of different form of dynamic network. Most people actually is talking about in the literature, talking about dynamic network more is we call it Granger is a causality network. Then generally mean is you have each slice represent one time point. So you have the dynamic, that means from time point. So this one is x regulate x, x1 regulate s1 by itself. Then there's maybe another is form simultaneous regulate x1 at the next time point. So then you can fit this structure, then get the dynamic Bayesian network, or that we have. So if you compare these two, then you still have a two slice model, but only is the difference is that you can see there's no inter-slide relationship. Everything is inter-slice. So this one have an inter-slide, but then you have completely it's a general form. This one we call is a second order regulation, because this one is only depend on the previous time point. But say a lot of biology have time delay. Actually, it's now depend only on its previous time point. Maybe it's for the go back level. Then the structure may be more complex. Rather than two slide, maybe you have a three slide that three order is the structure. So there's a lot of different form you can represent depend on the order, but in general, it's also go back to data, how it's what the data can support, what the data can capture, even though they have an n order. But in general, you can probably data only support second order of this interaction. So it's people talk about the Bayesian network, but actually really is a simple form of the second order Granger causality. So in general, this one this everything is regulated by itself. So at the time point t is y depend on itself in the previous time point. Then it's question C, when you have it's really have a parent, it's x. Well, this is the model fit better than just it's the autocorrelation. Then you can see whether this one is the decide whether this one is the parent or not. So you have whether it's the linear form in the continuous data, or Bayesian is a network. It can have discrete, so the capture information will be not linear. But it's the dynamic go to extreme of dynamic network, then it give you more flexibility. It end up still capture what is x, decompose x as time t, what the potential as a parent of this xt. So this one, if it's more general form, we can capture its dynamic. So this one definitely is a parent, will come from its previous time point. But if you have intrastructure, then it's also related to its time point at the same time point. Then what is the assumption of all these one? So what is the form you want to capture? Then really is to depend on the sampling time, and say it's a regulation or a reaction time. So if you have a sampling time, it's much faster. You have lots of samples, it's much faster than reaction time. Then it's a simple, it's two-layer, it's a classic dynamic Bayesian network, or it's called Granger causality network. Well, fine. So everything is dependent on previous time point. So if you have a sampling time exactly as your reaction time, then this one is the other form is okay. You can have some in the middle. You can use in this form or more general form. But in biology, if you don't have enough the power to do sample, most of the time we sample is a few minutes, an hour, a few days, but a lot of reaction happen in seconds. How we can capture that relationship? Then if everything relationship happen is much slower than sampling time, only thing you can capture that relationship have to go to this how this A related B have to capture this is a dynamic network. So everything have to go to this more general form. And then the next question is what's the order that really pure depend on your data. So this one, I think it gives you roughly is general form, and not specific to a specific question, how to do search, how to do optimization, or how to do a scoring function. But it's more give you probably kind of like a general question or clear some confusion, give you some idea. So it's the next topic I give you see was how to using this network or a general Bayesian network form to construct a biological network. So this one I would have to thank a lot of people. It's a collaboration, and so the Stephen Friend that used to be at Merck and the Sage, and got a lot of support. So we have a colleague at Mount Sinai and used to be from Rosetta. Then so it's Eric Shad and Bing is here and Jidong. So we have the next topic I talk about how the genetics and a lot of collaboration is from UCLA, from Jake's lab, and a lot of mouse model is from the University of Wisconsin. It's Alan and Mark is here. And a lot of East work have collaboration with at the UW, it's Berkeley and Princeton, and maybe the next one we'll talk about some is cancer work. Then have a lot of collaboration at either Mount Sinai or at Seattle. And the last one I really have to thank is all this funding support from Mount Sinai, and it's a generous donation from the Canary Foundation and Prostate Cancer Foundation, and some support from NIH and NCI.